Hello and welcome to my video lesson 4.7 on diffraction and interference. Eventually we're going to talk about the double slit experiment. So first, before we can do that though, we have to understand diffraction and then interference, and then when we put those together, that's how we get the double slit. Diffraction is the bending of a wave around a corner. This happens with water waves, as you can see in this image. Waves kind of come in. Okay, I'm going to try a different color there. Waves come in like this from the ocean, and then what happens is, most of this stuff kind of goes straight, but when it hits this corner, it bends, and you can kind of see that it has kind of this, or maybe somewhere here, it has kind of a line where it will bend to. It will bend somewhat around the corner, not all the way around a corner, but that depends on the wavelength, and we'll talk about that. But a better, just a diagram version of this is what you can see here. So the waves come in from the left, they hit a slit, a hole, and so they start to spread out. So this spreading out of a wave, this is a very thick, let's try that again. The spreading out of a wave is diffraction. That's the idea of diffraction. So it's when the light spreads out when it goes around a corner. And so that's why it bends, quote unquote, bends around a corner. So diffraction is only detectable when the opening is smaller than the wavelength, because the wavelength determines how much a wave will diffract. As wavelength increases, so does diffraction. Okay? So if the wavelength, if these waves are further apart, then when it gets here, it'll diffract more than it did before. Okay, so the diffraction increases, meaning this angle in here increases. Okay, so that's diffraction as basic of an explanation as possible. In Physics 20, we learned about constructive and destructive interference. This is an important concept that we have to understand for waves before we can talk about light as a wave. So if we have two waves, as we can see here, we've got wave 1, wave 2, and they both have peaks at the same time or same position, then those peaks add up. So this one had 2 and this one had 2, so it adds up to 4. And same thing with the down direction, the valleys, if they line up, then it lines up here, and that's why it's double the peak and double the valley. Now, what happens if we have waves of alternate frequencies? So this is up by 2 and this is down by 2. Well, up and down gets us back to 0. Well, this one's down and this one's up, so it gets back to 0. And you can do that all the way through. And so this is called destructive interference because it's canceling itself out or canceling each other out. And this one's called constructive interference because they're boosting each other. This would sound, if you're talking about sound, this would sound louder and this would sound basically silent. Alright, so very important concept. If two waves are in sync with each other, they will constructively interfere, giving large peaks and valleys. So this can occur at two distances, or certain distances from two speakers, if they're sending out the same frequency. So because the speakers are different distances from each other, maybe I'll just draw this out quickly. Okay, so if this is you, the person listening, and there's a speaker over here, okay, and there's a speaker over here, right? This one's going to have some sort of distance that the sound needs to travel. This one has some sort of distance that the sound needs to travel. And so as the waves come into you, they may be out of sync. So here it's coming up, here it's coming down. And so you can see they're out of sync with each other. And so at this position, it's going to be silent. Or if they were in sync with each other, then it'd be louder. So you can get this actually to do it either way, depending on where you are standing. Okay. If two waves are exactly opposite to each other, they will cancel each other out and arrive at zero amplitude. This happens with noise-canceling headphones. What headphones are actually doing is they have a microphone that is listening to the sound around you and pumping into your ears the exact opposite sound, the opposite frequency, like where instead of going up, it goes down, or instead of going down, it goes up. And so by doing that, you're able to cancel out the noise from your surroundings, which is pretty incredible. The speed at which we can do that is incredible. The concept makes sense, but the speed is incredible. You can also have constructively and destructively interfering things kind of happening at the same time. This is called a standing wave. This happens when two sound waves that are close together, we start to hear the beat of the wave. So here we're going to listen to the beat of the wave. You can kind of hear the wah 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 sound. Okay, we're going to maybe do that again. So again, what you're listening for is that wah 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 wah. That is the beat. That is because at certain points it gets quieter because they're destructively interfering, and at certain points they're getting louder because it's constructively interfering. This is because the two wavelengths are different, and so as one moves on, maybe I'll draw this first. Maybe I'll see if I can draw this. So here's my one wavelength, okay, and here's my other one, which is going to be, oh, I want to use a different color. Okay, it's not perfect, but I think you get the idea that at this moment here, they're going to cancel each other. And at this point here, they're both going to, boost each other. And you can see that sort of pulsing will happen multiple times. And depending on how close the wavelengths are to each other, that'll show up differently. But let's listen again to, or continue to listen to this beat. Okay, a pretty cool effect. Now, Thomas Young realized that all of those things hold true for waves in general. So, for example, water waves. And if that holds true, and sound waves, and if that holds true for those, then it must hold true for light, if light is a wave. So he decided to try these things together, diffraction and interference, and he created the double slit experiment. The double slit experiment is where he puts any wave, but really it's light, through two slits. Here's one, here's the other. You'll see that it will spread out from that slit, okay, or from this slit. Okay, actually maybe if I use two different colors I can show that better. So light will spread out from this slit. If it was just one slit, then this is what you would see. Okay, and you can see that the blue part that I've drawn here is light spreading out from that slit. But if I draw this one now, again, it still looks like diffraction, although I will say that this is showing an incorrect diffraction because, like we said before, technically this part wouldn't have any light. There's some sort of amount of bending around a corner and some amount that won't be bending around the corner, but it depends on the wavelength. So anyways, interesting, but whatever, not important right now. So you'll see that there are places where the blue matches with the red. There, and I mean you would see that would happen here as well. Here, it's not perfect, but again you can see it. Here, 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 and right down the center as well, which we call the central maxima or center antinode. And you can see that this will happen here, but if you were to continue this pattern and draw it a little bit more precisely, you might even be able to see another one showing up here as well. So it depends on the specific example, but you might have another result where on the next result n might equal 2 up here or down here. Okay, so this is the idea of the double slit. Now, what he did is he put a screen over here and then used light. He used light from the sun to shine through here. Okay, and the important thing is that the sunlight had to be all coming in the same plane for this to work. So it's all in phase with each other. Then when it goes through the slits, then you're going to have this interference pattern on the wall over here. Here, here, and here. On the wall, it shows up as bright spots. And between that, there are dark spots on the wall. He found there's a relationship between the distance to the screen and the spacing of the antinodes, or the maxima, and the wavelength of the light coming through. So here's the formula. It's important to note that the first equation relies on small angle approximation. So what this is doing is it's saying that, well, we know in the second equation, that's the correct equation. The second equation, sine theta equals, well, we know it's opposite over hypotenuse. And what it's doing in the first equation is it's kind of saying ahead of time that, well, what if tan, so to get, if we look at this diagram here, the theta is coming from this part over here. This is theta. Okay, opposite is the x, adjacent is the L. So, if we were to get that theta, how do we do that? Well, tan theta equals opposite over adjacent. Okay, so if we want to find theta, that would be theta equals, actually, and I'm going to write opposite, which is x, over adjacent, which is L. So tan negative 1 of x over L. And then we can put that in for theta. Now, if it's a small angle, then instead of writing sine theta, we could just write sine of hypotenuse. But the truth is that like when it's a big angle, the hypotenuse over here is not actually equal to the adjacent. Right? The opposite, those two are the same, but here, the adjacent and the hypotenuse are not actually equal. So we don't know the hypotenuse, it's hard to measure that. But if we knew it, we could just write in the sine ratio, opposite over hypotenuse. But since we don't know it, what they're doing here is they're approximating it, and they're saying, well, hypotenuse is close enough to the adjacent length. And you can see that in the diagram that it's going to be close. If the angle is really, really small, right, then you're going to have these two lines. Well, hypotenuse here is basically equal to the adjacent. But if you have a triangle that's looking more like this, well, now the hypotenuse is very different from the adjacent. So it depends on if that angle is tiny or big. Okay, so all that they're doing here is they're approximating this and they're saying, well, here, this is approximately this. And so then they just put this in instead of sine theta. So what they're doing is they're going like this, d over n, and then instead of sine theta, they're putting x over L, which you can see, hopefully, that this simplifies to that guy, just putting the L on the bottom. Okay, but we know that to not be true, so what we do instead, unless it's a small angle and it's a fair approximation, but what we do instead is we can solve for theta and then put it in for theta, and then we can get the right answer. So let's write that out. Lambda d over n, and sine of theta, but theta we don't know. We know tan negative 1 of x over L. That we know. That is theta. And that's the proper calculation. If they're a small angle, sine and tan negative 1 would cancel with each other. They're basically the same. But if it's anything bigger than 10, you really need to do this properly. So those are the equations. As we said earlier, the amount that a wave will bend around a corner depends on the wavelength. Since the wavelength of light depends on the colors, they found that the light had dots spreading out, but that the dots became a rainbow as it spread out. Okay, the light spread out more and more. So now we use diffraction gratings. You can see that sort of effect here, by the way, the spreading out of light. Red is diffracted more, violet or purple is diffracted less. We now use diffraction gratings instead of double slits because there are many, many lines, many slits, meaning that we get brighter results. But it's basically the same concept as a double slit. Okay, so this is kind of what that looks like. This is the screen, and you would get, like this shows, multiple lines coming away from the center. Whatever the center is, let's see if we can maybe say that. Let's say this is the center. We'll call that central node. Then this one would be N1, N2, N3, and it just spreads out from there. At some point, it either will disappear or become too dim, like either too far away, disappear, because it bends too far around the corner, or it'll become too dim for us to see anything. So in this one, it seems like we can see 8 of them. 8, 9, 7, 6, 5, 4, 3, 2, 1. Yeah, so I picked it right, picked the center one correctly. So it looks like we can kind of see 8 of them, but that's a lot. Normally we don't see that many with modern, really, really tight diffraction gratings. We normally don't see that many. So with all that said, let's try a couple example questions. Green light from a laser is emitted through a diffraction grating. The first antinode is at an angle of 1.2 degrees off of center. Considering this, what is the spacing of the slits on the diffraction grating? Okay, so some of these questions will be nice and simple. This is one of them. We're going to use the calculation like this. Okay, and we're looking for the spacing of the diffraction grating. Well, that's the D value. So all we're going to do is move everything over, except for D. Okay, so move everything over except for D, and since it's the first antinode, N is 1, since the wavelength is 533 nanometers, we have to write times 10 to the exponent -9. And then at the bottom we've got sine theta. Theta was 1.2 degrees. Make sure you're in degree mode, which we are, and we press enter. And we get that the diffraction grating is 2.55 times 10 to the -5 meters. So 2.55, actually, since we've got 2 sig digs, 2.6 times 10 to the -5 meters. Or another way to say that is to try to convert to some other potentially more useful measurement. So I think micrometers are times 10 to the 6. So that would be 26 micrometers. So that would tell us that every slit of the diffraction grating is 26 micrometers apart. Okay, so yeah, because on the formula sheet, micro stands for times 10 to the -6. So to switch this to micrometers, we would just divide by times 10 to the -6, which gets us 26. Okay, let's take a look at the next one. If the spacing of the first antinodes on a screen are 30 centimeters from center, while the screen is 95 centimeters away, and the diffraction grating has a slit spacing of that many lines per millimeter, what is the wavelength of light being used? So there are multiple kind of issues here, or things to notice. First of all, I would consider drawing this out. This is my center line. This is my first n equals 1 antinode. And so I'm drawing this to try to help myself visualize what's going on. This is theta, this is L, this is X. X is 30 centimeters. The screen is 95 centimeters away. And unfortunately over here is D, and D is annoying because it's not in meters, it's lines per millimeter, which is, yeah, kind of annoying. We have to, what we're going to have to do is go 1 over 550, and this is lines per millimeter, so it's millimeters per line now. So this gives us millimeters when we do this, but what we want to know is meters. So what we're going to do is divide this by 1,000, or actually better yet, multiply by meters on top and millimeters on the bottom, which is 1 over 1,000, so dividing by 1,000. But hopefully this makes more sense in terms of unit cancellation. So our spacing is 1 over 550, 1, 2, 3 more zeros, meters. That's how many meters apart it is. So it's a very small number. I'm not going to worry about writing as decimal. We'll just leave it as a fraction. Yeah, you could write it, but I'm not going to worry about that. Okay, so we have all that information. The thing is, we're looking for the wavelength of light. What you can see is that if you look at these two numbers, they're too similar to each other, which means that the angle is going to be relatively large, which means we cannot use the small angle approximation. We're going to use the regular d sine theta over n calculation. And what we're going to do here is notice, to find that theta, we have to use tan, because we don't know the hypotenuse. So tan equals, and then it will be opposite over adjacent, or x over L. So that changes to tan theta equals tan -1 of x over L. So d sine of tan -1 x over L, because that tan -1 is the theta in the question. Okay, so we've just replaced the theta with that. And what are we looking for? The wavelength. So actually we just have to type it in exactly as written now. So that's what we're going to do. So first of all, our D, which is 1 over 550,123, times by sine of tan -1 of x, which is 30. I'm going to write it in meters because I don't want to make a mistake. And actually it wouldn't matter if you kept them both in centimeters, that would be fine. But I don't want to make a mistake anyway, so let's do that. Over n, which is 1 because it's the first antinode, and so we get 5.4 times 10 to the -7. So 5.47, I think. 48. Hold on. 475 times 10 to the -7 meters. Again, we will be switching this to nanometers by noticing that nano means times 10 to the -9. So if you divide by times 10 to the -9, you get 548 nanometers. And this is reasonable for light, visible light. This will be like green light or something like that. Yeah, somewhere around green light. The issue is our sig digs are annoying because we've got 2 sig digs. So actually, for our own sake, we're just gonna fix this here, because normally in a question we would like it in nanometers. You could have the correct answer as 5.5 times 10 to the -7 meters, but that's not ideal. Nanometers is better. So that's why I'm going to change it to 3 sig digs. Okay, one more question to try out for this video. Pause the video now, try it yourself, and see if you get the same answer I do. A screen is placed around 5 meters away when shining my red laser pointer, 640 nanometers. What should the spacing be for the first 3 maxima for a comb, which has its slits 1 millimeter apart when used as a double slit? So what we're looking for is the spacing, that means the X. Now, keep in mind, when it's that far away, it's probably going to be a small angle. And we can try for now. If it's a small angle, we'll know right away because, like I said before, the L and the X, if they're similar in size to each other, then it's going to be big angle. If the X is much, much smaller, then it's probably going to be a small angle approximation. So let's try it out. The formula is XL. There you go. That is the formula, small angle approximation. We're going to rearrange and solve for the spacing between the maxima. So X, which means we're going to move N and L and D over. So we get X by itself. So what we're going to do now is say, okay, it depends on, it says the first 3 maxima. So what we're looking for is when N equals a value, 1, 2, or 3, what is the X distance? Okay, so we're just going to go ahead and plug those in. So lambda is 640 nanometers, so times 10 to the negative 9, times N, we'll get to that in a second, and times L, the distance to the screen, that's 5 meters. And then the diffraction grating distance, or the distance between the double slits, is 1 millimeter, so 0.00, that's centimeters. This is a millimeter. There. And so now this is a perfect equation. Now what we're going to do is multiply by N, which is 1, so 0.0, hold on, 0.032, and then the second one, we're going to do the same thing, except we're going to get 2, so it's 0.0064, and you're going to see a pattern here. It seems linear, right? It seems linear, and it should seem linear based off of the calculation. It is linear, assuming that it is a small angle. So interesting to note here, this linear relationship. Okay, so just for context, this is about 3.2 millimeters. Yeah, this is 6.4 millimeters. I was just thinking in my head to double check that. This is 9.6 millimeters. So it shows how close they are with a red laser pointer and a comb. So what you want to do is you want to get those slits closer together in order to get a better result. Alright, I hope that this video helps you better understand diffraction and interference, but especially the double slit experiment. I hope this video helped, and good luck.